Welcome back. Today we are dealing with a piston cylinder device. The initial volume of this device is 0.025 meters cubed. The initial pressure is atmospheric pressure at 101.325 kilopascal, and the initial temperature is 300 Kelvin. The area of the piston is 0.05 meters squared, and the mass that is placed on top of the piston is 100 kilograms and will be represented by this orange M box on the schematic. Now we want to determine what happens as this piston moves from state 1 to state 2, state 2 to state 3, and then from state 3 to state 4. The color of the gas inside the piston will be denoted by that darker color gray that you can see on screen right now. Now there are a few key assumptions we have to make before we start this problem. The first one being that this process exists under quasi-equilibrium. Second one being that no kinetic or potential energy changed during this process. The third one being that we assume that air is an ideal gas. The fourth one assuming that this piston is massless, frictionless, and leak-proof. And the fifth assumption we make is that no work happens other than boundary work. The equations we'll be using include the first law of thermodynamics. The equation for work equals integral of P dV. The equation that says the internal energy is equal to mc delta T. PV equals nRT, our ideal gas equation, and that pressure equals force over area. Now let's get into the analysis from state 1 to state 2. Our very first step is to determine the mass of the air, and this mass will stay constant as this is a closed system. So the mass can be calculated using the ideal gas equation, which is mass equals PV over RT. When we sub in our givens, we determine that the mass of the air, which remains constant, is 0.0294 kilograms, and from now on, mass of the air will be denoted by letter M. Now, to determine the pressure at state 2, we need to take the pressure at state 1 and add the change in pressure. And the change in pressure is calculated by taking the force acted upon the air divided by the area of the piston. When subbing in for the mass and gravity, which is our force downwards, and the area, we get a pressure 2 of 120.925 kilopascal. Now, to determine the volume at state 2, we go back to our ideal gas equation, setting up for V this time. And when we plug in all the values that we have previously determined or have been given, we learn that the volume at state 2 is equal to 0.02094 meters cubed. Now, to calculate the work from state 1 to state 2, we use our equation that says that the work is equal to the integral of P dV. Now, when we replace P with mRT over V, which is from our ideal gas equation, and then we solve our integral and plug in the little values we have here, we determine that the work is equal to negative 0.448 kilojoules. And as this work is negative, it means the work is being done onto the system. And that can be clarified better by looking at our schematic and seeing that when we go from state 1 to state 2, the air is being compressed and work is being done onto the system. Now, to determine the heat transfer from state 1 to state 2, we go to the first law of thermodynamics, which states that the net heat transfer minus the net work is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. Now, we made the assumption that both kinetic and potential energy changes are negligible here. And we also will say that the net internal energy is also zero because our temperature is constant and internal energy is a function of temperature. Now this leaves us with Q equals W, so our heat transfer is the same as our work rate, which gives us Q equals 0.448 kilojoules, and because this is negative, it means that the heat is leaving the system. Now moving on to the analysis from state 2 to state 3, there are a couple key things we must note before moving on. We must note the pressure at state 2 and the pressure at state 3 are the same, as they're both experiencing atmospheric pressure and the mass of the cube does not change. Another thing to note is that CV is given in the problem. Now, to calculate the temperature at state 3, there are a couple key things we need to go here. Now, as you can see at the very top, we have our simplified first law of thermodynamics. In purple, I have highlighted work, and in green, I have highlighted the change in internal energy. Now, when we take the equation for work, we know that W equals integral P dV, and we know that P dV is V3 minus V2. So P dV is P V3 minus V2, and that leads to delta V. And we know from our ideal gas equation that P delta V is equal to mR delta T. Now keep that mR delta T in mind. Jumping to the delta U, we know that delta U is equal to mc delta T. Now when we take those two equations and plug them back into our first law of thermodynamics, we get that our Q, our heat transfer, is equal to mc delta T plus mr delta T. Once we've kind of simplified that equation, we get to the point where we can say that Q is equal to delta T times mCV plus mr. Now CV is given in the question as stated previously and is equal to 0.7176 kilojoules per kilogram Kelvin. Now when we plug in all the variables that we've already solved for, we see that temperature at state 3 is equal to 706.49 Kelvin. Now to get the volume, we go back to our good friend the ideal gas law. And when solving for volume again, while plugging in the variables that we've already calculated, we get that the volume at state 3 is equal to 0.493 meters cubed. And now for the work rate from state 2 to state 3, we go back to how we solved earlier, that work is equal to P delta V. And when we plug in for P and delta V, with the V3 and V2 that we calculated previously, we learn that our work is equal to 3.43 kilojoules. And since this is positive, that means work is being done by the system. And this is made clear in our schematic here, where we can see that the volume expands from state 2 to state 3. And our heat transfer is given already as 12 kilojoules in the question. Now moving on to our analysis from state 3 to state 4, one thing we must note is that the volume remains constant here, so V3 is equal to V4. And we also are told in the problem that pressure at state 4 is equal to the atmospheric pressure, which is 101.325 kilopascals. To determine the temperature of air at state 4, we go back to our ideal gas law, this time isolating for temperature. And when we plug in our pressure, volume, mass, and our gas constant, we get that temperature at state 4 is equal to 591.2 Kelvin. To determine the work and heat transfer from state 3 to state 4, we first take our equation for work, which is integral P dV. And since our volume is constant, there is no dV, there is no change in volume. So the work is 0. And you can also see this in the schematic as you see that no work is being done on the system or by the system, as the piston remains constant and is locked. Now for the heat transfer, we take our equation mCV delta T, and we know the mass, we know CV, and we know delta T. We plug those in, and we get that our heat transfer equals negative 2.419 kilojoules. And as this is negative, it means that heat is being lost by the system. Now, we have to check if the assumption we made in the beginning, that air is an ideal gas, is an accurate assumption. To check that, we go to our table A1, where we get our critical temperature and critical pressure values. And then we compare that with our calculated temperature and calculated pressure values by dividing temperature over critical temperature and pressure over critical temperature to give us reduced temperature and pressure. Now when we make our table of reduced temperature and reduced pressure values, we see that our reduced pressure values are generally less than 1 and quite less than 1, and our reduced temperature values are generally greater than 2. This means our assumption of the air being an ideal gas is a safe assumption.